Given n samples from a uniform distribution 0 to d, how would you estimate d? This is a question which was asked for a data scientist role at Spotify. So what does this question say? We have n samples. Let's denote these by x1, x2 till xn. We are told that these samples come from a uniform distribution. So xi comes from a uniform distribution denoted by u between 0 and d. And we are asked how do we estimate d? So let's say this is 0, this is d on the x-axis, this is the y-axis, this is our distribution. This would be 1 over d because this is a uniform distribution. And all of these points xi are somewhere in this range over here. Now, this question will test your understanding of maximum likelihood estimation. So let's go ahead and see how we solve this. Quick recap of the question, the information we are given. X is the data points which we are given. These are uniformly distributed between 0 and d. The PDF of a uniform distribution between 0 and d would be given by f of x equal to 1 over d, where x is between 0 and d. Now we are given some data points, which is x, and we are given a distribution from which the data comes from, and we don't know the parameters of the distribution. So the approach to estimate the parameters of the distribution given the data, we use the maximum likelihood estimation method. So the likelihood of observing all the samples is given by, we call this function L, where d is the parameter. This likelihood function would be the product of f of xi for all I. Now, what does this mean? So we have the PDF given by f of x, which is the probability of observing a given data point x. So we are given n data points. So if we were to ask what's the probability of observing the first data point x1, that would be f of x1. Then what would be the probability of observing the second data point, which is x2? That would be f of x2, and so on till the nth data point xn. And what will be the probability of observing all of these together? That would be the product of all of these probabilities. And this would give us this likelihood function over here. Now, f of x, the PDF we saw for a uniform distribution between 0 and d is given by 1 over d. So the product of 1 over d n times becomes 1 over d to the power n. So L d, which is likelihood function, becomes 1 over d to the power n. Now we have the likelihood function L of d, which is given by 1 over d to the power n. We have to maximize this likelihood function, which basically means we have to maximize the likelihood of observing this given data set, and we have to find the value of d that would maximize this likelihood. So here, if you see in this function, d is in the denominator. So to maximize this function, we want d to be as small as possible. But d has to be at least as large as the largest value of x. So t must be as large as the largest observed sample point. So d is greater than or equal to the maximum of xi, which means that the optimal MLE estimate is given by max of xi. But is this a biased estimator? Before we answer this question, let's understand what is a biased estimator anyway. What is a biased estimator and why should you care about bias? Bias tells you whether your estimation procedure systematically overestimates or underestimates the true value. So let's say you have a distribution like this, where your true value, the true distribution, is something like this. Now, the true value, true expected value, which lies over here, is larger than the expected value that you are estimating. This is what the bias is. In this question, y is the maximum likelihood estimate which we saw, which was d equal to max of xi. Why is this biased? So the maximum can never exceed the true endpoint. If let's say the true endpoint was 100 and we observe values like 63, 98, 91, 95, and so on, we take the maximum of these. The maximum is still 99. It can never exceed the true endpoint, which is 100. So our estimate will be consistently lower than the true endpoint. So the maximum is always less than equal to 100, usually slightly below 100. It almost never equals exactly 100 for continuous distribution. So naturally, the expected value of max of xi will be less than 100. So this is where the bias comes from. It comes from the fact that the sample maximum almost never reaches the true endpoint. Now, how do we estimate the bias? How do we quantify it, and how do we then estimate the unbiased estimator? To do that, we we say that let's assume m is a random variable, which is the maximum of all of the xi which we have in our data set. What we'll do is we'll first find the CDF of m, and then we'll differentiate it to find the PDF of m, and then we'll find the expected value of m. So let's go ahead. So to find the distribution, we first compute the CDF, denoted by capital F. M is our random variable. X is equal to, this is the standard procedure for finding the PDF of a random variable. We define it probability that m is less than or equal to x. Now, probability that m is less than or equal to x. What is m? If you remember, this was the maximum of all of the data points xi. So if the maximum is less than or equal to x, which means it means that each of the points x1, x2 till xn are less than or equal to x. So we write this as probability that x1 is less than or equal to x, x2 less than or equal to x, till xn less than or equal to x. Since the samples are independent, we can write this expression probability that x1 less than or equal to x, comma x2 less than or equal to x, till xn less than or equal to x, as probability that x1 less than equal to x times probability x2 less than equal to x, and so on till probability xn less than equal to x. This is what is written over here. Now each xi is uniform over 0 to d. So this is, let's say, 0. This is d. This is 1 over d. This height of this rectangle is 1 over d. And let's say this point here is x, small x. So what would be the probability that xi is less than equal to x? It would be this area. Yeah. And what is this area? It would be this width, which is x, times this height, which is 1 over d. So it would become x times 1 over d, which is x over d, which is what we have here. So the CDF becomes f of x of m is equal to x by d to the power n. This is where x is between 0 and d. So now we can calculate the density by differentiating the CDF. We differentiate x over d to the power n. This gives us n times x to the n minus 1 over d to the power n. Now we can easily calculate the expected value. Is x times f of x dx integrated from 0 to d. So f of x we have over here. We multiply this with x. So this would become x to the power n. And then x to the power n integrated would become x to the power n plus 1 over n plus 1. And the limits would be 0 to d. And n over d to the n is the constant part. So we put the upper limit. This would become d to the power n plus 1 over n plus 1 and over d to the n times d to the n plus 1 over n plus 1. So this d to the n would cancel out, and this would give us n over n plus 1 times d. So we have the expectation, which is expected value of xn is n over n plus 1 times d. So what does this mean? Let's say this is a number line. We have d over here, which is the true value. This is what we had to estimate. We said that our estimate of d is max of the xi's. This was our estimate. Then we checked whether this estimate is biased. And how did we check? We said that this, let's say this is a random variable m. We'll see the distribution of this random variable, and we will see what the expected, where does the expected value lie. Then we'll see if this expected value, does it lie away from d or not. And as it turns out, this d is n over n plus 1 times d, which means it's lower than the true d, which we have here. Which means if this was the true d, the estimated d would lie somewhere over here, which is lower than the true value, which is n over n plus 1 times d. Which means our estimate would systematically underestimate the true value of d. And it's obvious, as we saw, the maximum could never exceed the true value and it would almost always be lower. That's why our estimate is also biased on the lower side. So how do we make our estimator unbiased? Well, we simply multiply our estimate by n plus 1 over n. So this would give us d, which is equal to n plus 1 over n times xn. So to summarize, the MLE estimate was the maximum of the xi's. This was a biased estimator. The unbiased estimator is n plus 1 over n times the maximum of xi's. And we already went over the proof, the derivation. We calculated the CDF, then PDF, the expected value. We saw how the distributions, the expected value of the maximum of xi's was lower than the true value of the parameter d. So this is our unbiased estimator and this is our biased estimator. So this is the final answer to this question. I hope you like the video. If you like to read more questions, check out datalooper.com. Thanks for watching, and I'll see you in the next video.